Well, we just left off the first couple pages of 3.4 discovering that we can find eigenvalues that appear to be complex with imaginary parts, but what does it mean for the eigenvectors? And so that's the tricky part. Just a reminder that if we have eigenvalues, if we find eigenvalues, then those eigenvalues have to make this equation true. That's our basic equation of take your coefficient matrix, multiply it by some eigenvector values, x1, y1, and that must be equal to the lambda value times that eigenvector. These two things must be equal in order for lambda to be an eigenvalue. So let's try it out. Let's try it for our lambda 1 from the previous page of -2 plus 3i. And so just a reminder, our coefficient matrix was -2, 3, -3 up here, +3, and then -2. And what we're saying is that times some eigenvector, values of which we don't know for x and y, must be equal to -2 plus 3i times x1, y1. Now, if you're sitting there thinking, oh boy, what am I going to do with that I? We're just going to treat it like it's an algebraic quantity. The only thing we have to keep in mind is, I'm just going to add to the side, to recall that I times I is equal to -1. And 1 over I is equal to -I. And if you want kind of proof for where that comes from, how that happens, if you imagine multiplying top and bottom by I, in the denominator you'd have -1, and the top you'd have I, so it would be -I. So that's an important thing for us to keep in mind. This is kind of the rules of the road when dealing with imaginary numbers. Right? So over here, remember, this is going to turn into two specific equations. One of them is going to be the top equation, right? Which would be -2x1 minus 3y1. And on the other side, that's going to be equal to this thing times x1. So -2x1 plus 3i x1. And the bottom equation will be 3x1 minus 2y1. And that's got to be equal to this thing times the bottom here. So -2y1 plus 3i y1. Now, on first glance, you might think, well, these two equations are absolutely nothing alike, right? You've got the I is attached to a different variable. They couldn't possibly tell us the same thing. And that's the rule for finding our eigenvectors. These two equations really have to tell us either the same exact thing, like y equals 2x, or they have to tell us something ridiculous, like 0 equals 0. Not ridiculous in the logical sense, but just like unhelpful, something that's obviously true. So 1 equals 1, or 2 equals 2, or 0 equals 0. If you get a result like that for one of the equations, that's okay. The other equation's just going to tell you the relationship. So at this point, you might be thinking, well, they're not the same thing, but let's try to manipulate a little bit. Let's do a little bit of algebra here, complex algebra. So for this one, I'm going to try to get all of my y terms to this side and get all my x terms to that side. So I'm going to leave the y1 here, the -3y1 on that side. And by moving this -2x1, oh, there's a -2x1 over there. Those go away, and I'm left with just 3i x1. So the first equation boils down to this. The second equation, I'm going to try to do the same thing, get my one variable on one side and the other variable on the other, but I'm going to do it kind of backwards. I'm going to leave my y1s here on this side, or excuse me, my x1s on this side, and so 3x1. And then when I notice I've got the -2 and the -2, those go away, and on this side I've got 3i y1. So again, you might look at that and think, those are absurd. They're totally not the same thing. But I think you might be surprised. They actually are. So we're going to take this top equation, I'm going to take them kind of one at a time. And if I simplify this, kind of divide both sides by -3, we have y1 equals negative I x1, right? But what about the bottom equation? If I want it to be y equals something in terms of x, I want to solve this thing for y, that means I'd have to divide both sides by 3i, not just by 3, but by 3i. So this thing would be y1 equals, divide both sides by 3, those go away, it'll be x1 over I. And if you remember the rule, 1 over I is the same thing as multiplying by -I. That really is negative I x1. So on first glance, you might think, oh, those are totally different, but they're actually telling you the same thing. And what they're telling you collectively here is that the eigenvector that's associated with this complex eigenvalue is whatever you plug in for x, the y value will be -I times that. And so normally when we read eigenvectors, we'd say something like, oh, so that means go right one, and then how do you go down an imaginary amount? And the answer is, you can't. You can't read this on the plane because it's not an xy planeable thing, right? And so this eigenvector can't be interpreted physically the same way that we're used to. So that's great. What does that mean? Excuse me, what does that mean about our eigenvector number 2? So I'm going to squeeze this in right underneath what we're doing here and say, what about lambda 2 equals -2 minus 3i? Since we have 2 eigenvalues, you'd think that we're going to have 2 eigenvectors. So what happens? Well, if we plug in the numbers, we're going to get 2 equations. This time, I'm just going to kind of go off this top one. It would be -2, -3, 3, -2, and then x1, y1. The other side is going to be -2 minus 3i because they're conjugates. And so the question is, what do, oh, sorry, and I'm not labeling these all x1 and y1. They should be x2 and y2. So when I create my 2 equations from this, you're not at all going to be surprised to find that they don't initially look the same. So -2 x2 minus 3 y2 equals -2 x2 minus 3i x2. In the second row, 3 x2 minus 2 y2 equals -2 y2 minus 3i y2. Right, and so this looks very similar to what we had before. As a matter of fact, these 2 equations are identical except right here. There's the difference. Instead of that being a plus, now it's a minus. So the difference that this makes appears here. I'm just going to kind of track it for us so that we can keep an eye on it. And so what does that mean for what these equations are equivalent to? Well, my 2, oh boy, that's a terrible bracket. Shh, don't tell my 3rd grade teacher, she'll yell at me. We wind up with a little bit of manipulation. You notice the 2x2 or -2x2 on both sides, that goes away. We can divide both sides by -3, and we're left with y2 equals I x2. And in the bottom, the -2 y2's go away. And if I want to divide both sides by -3 here, I'd wind up with y2 equals -x2 over I, which we know dividing by I is the same thing as multiplying by -I. And so this really is the exact same thing. Negative I x, oh sorry, the negative and the negative cancel. Sorry, I'm getting ahead of myself. I x2. So what does that mean for our second eigenvector? Well, that means our eigenvector number 2 would be equal to whatever you plug in for x, out pops I times x. So I. And in both cases, you get the same result. So taking a look at our two eigenvectors, you should see they are suspiciously similar. They are exactly the same, except their imaginary terms are opposites. We would say that they are conjugates of each other. So just like the eigenvalues are conjugates, the eigenvectors are also going to be conjugates of each other. So what does this mean associated, or mean for the particular association, or with the first eigenvector and eigenvalue? Well, that means straight line solution, for what it's worth, I'm going to put little quotes around it. Straight line solution number 1 is going to be equal to e to the negative 2 plus 3i times t times its eigenvector, which was 1, negative I. And the straight line solution number 2 is going to be, oh, sorry, I'm writing it like you can't see it. y2 e to the negative 2 minus 3i t times its eigenvector, which is strangely similar, just not minus. So again, tracking that negative, what happened? Well, it made this a, oops, sorry, it made that a positive, right? Made this a positive, which had an effect down here. So the complex conjugate aspect of things only appears in a very small little bit of a place. So these are quote-unquote straight line solutions, but they're kind of meaningless to us on the xy plane because the xy plane is real numbers, and these are not real numbers, right? These are complex numbers with imaginary parts. So there must be some way of rewriting the solution, because these actually do check out. If you were to plug this in, if you were to plug this into the original equation, you'd find out that that one checks out. And this one also checks out. Both check out when substituted back in. Into the matrix DE. And so this is the really frustrating part, because you look at it and you think, well, how could they possibly check out? They're complex, right? Well, what happens during the process when you're plugging them back in, taking the derivative of things and kind of multiplying things out, the complex numbers just kind of, they get canceled out basically along the way. And so they kind of take care of themselves. So what do we do with that imaginary number in there? There's got to be a way to rewrite this solution. And so what we're going to do is we're going to rewrite these straight line solutions in terms of the real numbers. And that's what we're going to do next in the next video. We're going to rewrite these straight line solutions that are 100% correct, but we're going to rewrite them in terms of the real numbers. So I'll see you there for that.